Hi everyone, welcome to the final presentation of Team 7. I will introduce the first part of our project overview. The goal of our project was to build a production-ready, scalable, and fair movie recommendation system. The system had to handle real-time data, support A/B testing for experimentation, and remain reliable end-to-end. The dataset comes from streaming platform with 1 million users and 27,000 movies. We ingest real-time user behavior like watch log, page views, and ratings through Kafka. Metadata include demographic details like age, gender, as well as movie genres and popularity. On the modeling side, we're focusing on SVD, collaborative filtering, and KNN. We use MLFlow to check experiments, virtual models, and manage retraining workflows. To ensure model performance, we run both offline and online evaluation. We also conduct A/B testing to ensure the behavior on users. We also conduct fairness analysis to make sure recommendations will not bias against any groups. The model will deploy it into Dockers, and we monitor everything with Grafana and set up alert for real-time failure detection. Git workflows ensure clean, reviewed code throughout the project.
Hi, I'm Gilbert. Now that you have seen an overview of our recommendation system, now I'll walk you through some of the key design choices that shaped how we built and developed our pipeline. First, we adopt a VM-based setup. We deployed all components, including training, evaluation, and monitoring, on a single virtual machine. This centralized setup made it easy to iterate quickly and debug issues across the entire system in one place, without the complexity of managing distributed infrastructure. Next, we chose to use a PostgreSQL database to store all processed data and metadata. This allowed us to run structured queries efficiently and ensure seamless integration with both our pipeline and our monitoring tools. We also use Docker for containerization, which helped us maintain consistent environments across the team. With Docker Compose, we were able to orchestrate multiple components like Prometheus, Grafana, and our ML pipeline smoothly within the VM. Finally, to monitor model performance and system health, we integrated Prometheus and Grafana. These tools allowed us to track metrics such as API errors, latency, and prediction volumes in real time, and trigger alerts or retraining workflows when necessary. With this setup in place, I'll now hand it over to Jahao, who will walk you through how all these components fitted together in our end-to-end pipelines workflow.
Let me let me walk you through our workflow. So our workflow start from data to model deployment. Everything start with the real-time data streaming coming through Kafka, and the data goes through ETL and data pre-processing, where we clean and format it so it's ready to be used. After that, pre-processing data is stored in the PostgreSQL, which acts as our main database. From there, we can either serve prediction, use our existing model, or kick off retraining when there is enough new data or performance starts to drop. Once we retrain, the new model gets to register in our model registry. This where we keep track of our model vision. The load balancer then manages traffic and route incoming requests to either the old model or the newly trained one. We run both parallel so we can test the new model while keep the old one alive just in case. Finally, we use the Prometheus to collect the metric from both model and then use Grafana to help us visualize everything so we can monitor performance and spot any issue quickly. This setup gave us a reliable, flexible pipeline that supports continuous model improvement while keeping production stable.
Hi, my name is Pochin Chen, and I'll be talking about the technical challenges we faced in our project. So there are two main technical challenges. The first one is containerizing, monitoring, and CI/CD. So what I meant by that is like these are the three main aspects of our project, which is like it's properly containerized, properly monitored, and there's a proper CI/CD pipeline behind it. But that's also quite challenging to work with because these three are sort of like interdependent or interdependent or interconnected with each other. So whenever we want to like work on them, we have to like take all three into account when we develop code for them. So the second challenge is the security concern. So one of our peers, one of our classmates, had their had their VM hacked because they had a weak Postgres password and also an open port to the outside, so which prompted us to look deeper into our security measures. So but it is quite hard to. It's quite challenging to do it properly because there are a lot of things to consider. So at least we try to like properly enforce the users' rules, and also like keeping credentials secure, like using passwords instead of the default ones, changing out the passwords instead of using the default ones, and also like dabbling with the firewall configuration on our VM. So yeah, these are the main technical challenges we face.
Next, we move on to reflection and future works. So, one thing we definitely do differently next time is setting up the system to handle regular model updates from the get go. We kind of added retraining and rollback features a little late in the process, which made the iteration slower. And so, going forward, we would have all of these deployment tools in place early. Second, we also learned that good monitoring can't be an afterthought. And there were a few moments when we noticed issues like latency spikes or weird recommendation behavior. And we realized that we didn't have the metrics to fully understand what was going on. And so, next time, logging and alerts are should be there from like day one. Also, our system worked fine, but parts of it were too tightly connected. And in the future, we try breaking things into smaller services like separate components for training, serving, and logging, wherein each piece can work without affecting and it's less monolithic. And lastly, we didn't fully prepare for all the cases like model drift or missing data, and when things broke, and it took time to figure out why. So for the next version, we'd also focus on having some fallback models so that the system stays stable even when something goes wrong.